Buffer lecture video 2. So we left off with this problem right here where I was asking you to calculate it, and hopefully you saw that this tweaked it just a little bit. It was like 4.75 or something, and then when you added this it was just enough to go up to 4.77. So it will change the pH, but you can see how slight it is. Okay, so to make sure we got the hang of this, let's do the same thing with this salt right here, ammonium chloride, and this nice nifty little weak base. So this one's going to give us a Kb value, and so the first thing they ask you to do is find pKa. So, because you're going to need that as part of that Henderson-Hasselbalch equation. So what you need to do is take the Kb and turn it into a pKb, but you're still not there yet. Okay, so we're going to use that very familiar equation, and then the two of them add up to be 14. So the pKa value is 9.26. All right, so now we're ready to start crunching those numbers. You take the 75 grams, do the whole shooting match to begin with of ammonium chloride to figure out exactly how many moles you have. And again, they give you the volume, not exactly 1 liter this time, but 1.22 molar NH4 plus. So now you've got that salt, or that conjugate acid. You can see it has an extra hydrogen to give, so it's a conjugate acid. So for finding the pH, you got the pKa, which we just figured out, is going to equal the weak base over the conjugate acid on the bottom right there. So it's always base over acid, and when you get that, it's 1.25 over 1.22. You take the log of that, that's going to change it again very, very slightly. Okay, but that's important that you show all that, and you show why it's not 9.26 anymore. It's 9.27. All right. So we have these two buffers in this next problem here. Notice that they are both 0.5 molar. All right, and in the second solution, they are both 1.5 molar. So you can probably guess from what I told you earlier that which will be the greatest change in pH based on when I talked about the strengths and the capacity of a buffer. So this one has more capacity to be a good buffer. You know that already, but we'll get to that coming up here. So this is important. Both solutions have this 1-to-1 ratio. Okay, so if they have a 1-to-1 ratio, then this portion right here is going to not mean anything. So the pH equals the pKa, because that's going to be log of 1, which is 0, and so it'll just be a pKa of 3.14. So, and remember that was given to you, so now I know the pH of the solution. So for part B, the first solution will experience the greatest decrease in pH. That's because the other one's stronger and has a greater capacity. The buffering capacity of this solution was exceeded, so the pH is going to change. All right, because you added too much Buffers are not limitless, okay? You can have a stronger buffer that'll resist changes greater, but once you pass that, then yeah, the pH is going to change. And the second solution will experience very small because it was a much stronger. You had 1.5 moles available to act, so you had an excess really of the fluoride ion to scarf up all the hydrogens. So hydrogen then becomes the limiting reactant, and this one could take on more hydrogens, and the pH still wouldn't change. So there are limits, and this problem shows that pretty well. All right, this next section, just a real quick review. You got hydrobromic acid containing acetic acid and its salt. So that's a buffer reaction. So you got to know what the business parts of this are. Of course, hydrobromic acid is a strong acid, so we just go right to the H3O plus, forget about the bromine. And then the salt of acetic acid, you just have to know, is acetate. It's a real common one that they use. All right, and of course, then this will scarf up the extra hydrogen and making that water. Okay, I'm getting a message that my battery's running low. There we go. Problem fixed. Plugged in. Okay, so try this one on your own. Little review of how to do this same thing. Hit the pause, write that reaction out. Boom. Hopefully you saw that the hydrofluoric acid is weak, so it's still intact as HF, and it's just the OH in the strong base. Now that's going to rip that hydrogen away from the HF and leaving you F minus H2O liquid. Nothing new here. Okay? So hopefully you're feeling pretty comfortable with those reactions. Now, indicators can kind of be substituted into like an acid-base equation. I'm not super huge fan of the way that they wrote about this, but just know that what happens is you get an indicator simply is a lot of times it's just a biological molecule like a plant or and it changes color at different pHs. So when it has the hydrogen, it's one color, and when it loses the hydrogen, then it's a different color. All right. So you can shift this back and forth. That's how we're going to help us pick out indicators based on where the equivalence point is. Okay? So that's what you want in a good titration, is to get an indicator that's real close to that equivalence point to make those things roughly equal. All right? Because when you get this, these two concentrations being the same, then pH equals pKa, and the indicator should be the pH of the equivalence point. So circle that, and that's the key idea. And then it becomes really straightforward to answer these questions. If you know the pKa's of the indicator, all you have to do is find out what the equivalence point is, see our lecture on titrations, and once you know the equivalence point, then you would go back and you'd say, I'm going to think bromethymol blue is a good indicator. And sure enough, bromethymol blue is yellow, and it turns blue right in the middle of that big change in pH. Okay, so that one worked out good. So if you have something like this, so it's a stronger base, okay, and they might not even give that to you. They might make you figure out that a strong base and a weak acid is going to be on the high end. So, you know, they'd have a, would this one be better, would that one be better, or would that one be better? And the answer would be this one, because right now we know it's closest to that 9.1. So phenolphthalein indicator that some of you used in the lab on our titration. Okay, so that is really very straightforward to do. Okay, now when looking at pH, pKa, HA, and A minus as a group here, now these two slides are very close. So you want to see what the differences are. So if you have a small number on the top, so just think of this bottom one as the acid and the top one's the base. If you have a small number on the top and a bigger number on the bottom, when you do the log of that, it's going to be negative, okay? And that will cause that the relationship between the pH and the pKa to change appropriately, okay? So, and then this one is, if you have the bigger number, then this is going to be positive, so the pKa will be higher than the pH. So, that leads to questions like this when the pH is 4.43 and the pKa is 9.91. You know the pH is lower. Therefore, what you're going to want is you're going to want that bigger number on the bottom to make this negative. So when you add a negative number to the 9.21, you can make it closer to the 4.43. Okay? So that's how you kind of work these problems in reverse. All right? So given that, let's see if you can figure out this one as to which one should be greater. Hit the pause. Welcome back. This one was a little tricky because we have to do pH versus pKa. So hopefully you saw that I needed to change that. So the pKa is 7.95. It won't change your reasoning very much because it's still the pH is still higher than that. So because of that, the pH is greater than the pKa, and that means you need a big number to make this positive so that you can get these two things to be equal. Okay? So a little tricky, but that is something that you should walk through the reasoning on this. Again, you want those things to be equal, or think of them as getting equal, and that's how I do it. It makes a lot of sense that way. So you need this big number over small number to make that positive because the pKa was too small. pH is big. All right. So those are some of the problems, and you can look those over. I'll post the answers, and so that is our acid-base unit. All right, congratulations.